Hi Honors Algebra 2 students. Today we're in Chapter 5, Day 6 notes, and we're going to do a variety of topics in this lesson. So the first thing we're going to do is solve quadratic equations using the square root method. All right, so before we get into the specifics of the first example, I want to mention when using the square root method to solve a quadratic equation is useful. So if you have just a squared term and a constant, that's when you can use this method. If we tried to use quadratic formula on this one, we certainly could, but it would be a lot of extra work. And if we tried factoring this one, we wouldn't be able to factor it. So if we've got just a squared term and a constant, as we do in this first example, that's when we would want to use square root method. Again, we could use quadratic formula, but it's a lot more work in this particular case. So let's take a look at how square root method works. All right, so the first thing we want to do is isolate the squared term. So I want to isolate this quadratic term, and truly, I want to get it so that it's a positive 1x squared equals something. So the first thing I'm going to do is I'm going to divide both sides of the equation by 3. So I get x squared is equal to 8. And then once I have a positive 1x squared, as I do right here, then I'm going to take the square root of both sides of the equation. So the square root of the left-hand side, the square root of the right-hand side. Now I need to put a plus or minus in here when I do that. And I'm going to come back and explain why I need to do that in just a moment. I'll give you another little side example so you can see why I need to do that. But let's finish this one off in the meantime. The square root of x squared is x. And if I simplify the square root of 8, that is 2 root 2. So my final answer is x equals plus or minus 2 root 2. Again, if I would have used quadratic formula for this one, I would have first had to have gotten the equation set equal to 0, and then I would have had to go through quadratic formula and completely simplify it. It would have been a lot more steps as opposed to using this method. Okay, so let's do a little sidebar here. Here's why I needed to put the plus or minus in there. Let's say we had x squared is equal to 4. I think everyone would agree that I could get an answer of either positive 2 or negative 2. Because if I square a positive 2, I get a positive 4. If I square a negative 2, I also get a positive 4. So in other words, this squared term is going to produce two solutions, in this case positive 2 and negative 2. So I need to make sure that if I'm solving a quadratic equation using the square root method, when I take the square root of both sides of the equation, I need to remember to put that plus or minus in there. That's where I'm going to get my two answers. All right, next example. When we use square root method, we're going to look at all of this as being our term that's squared. So we need to isolate our term that is squared, our quadratic term, and in this case, it's already isolated. So I can immediately go to the step of taking the square root of both sides of the equation. So take the square root of the left-hand side of the equation, take the square root of the right-hand side of the equation, remembering to put my plus or minus in there. All right, now the square root of anything squared, so the square root of 2x plus 1 quantity squared is just going to be that quantity 2x plus 1. So in other words, the square root of anything squared is just the anything. So that will be 2x plus 1 on the left-hand side. And then the right-hand side is plus or minus 6. Now I still need to solve for x. So 2x plus 1 could equal a positive 6 here. 2x plus 1 could equal negative 6. So 2x is equal to 5. X is equal to 5 halves. That's going to be one of my answers. And then over here, if I subtract 1 from both sides, I get 2x equals negative 7. Divide by 2, x equals negative 7 halves. All right, so just to reiterate, if I had used another method on this, I would have first had to have FOILed this out, then gotten my equation set equal to 0, and then gone from there, so to speak. In this case, it would have factored with answers like that. It would have factored, but regardless, even before attempting factoring, there would have been a lot of preliminary work that would need to have been done. So again, I'm just trying to emphasize why square root method is a good method to use on these. Again, if we have only a squared term and a constant, that's when we can use it. All right, in our next example, we have indeed only a squared term and a constant, but we do need to isolate this squared term first. So just like we did in the first example, we're going to do something comparable in that we're going to divide both sides of the equation by 2. So we get x minus 3 quantity squared is equal to 18. Then I have my quadratic term, so to speak, isolated. I have a positive 1 in front of it. So I'm going to now take the square root of both sides. Square root of the left-hand side of the equation, square root of the right-hand side of the equation, remembering my plus or minus. All right, the square root of a quantity squared is just whatever is inside that quantity. So in this case, x minus 3. I can simplify square root of 18 to 3 root 2. And then finally, to isolate x and solve for x, I need to add 3 to both sides. So x is going to be equal to 3 plus or minus 3 root 2. All right, and just a reminder, I am not going to combine the 3 with the 3 root 2. Those terms are not alike. In order for them to be alike, they would both have to be, for instance, root 2 terms. So my final answer is going to be 3 plus or minus 3 root 2. And again, just to put it in perspective, if I would have done this with another method, I would have had to have first FOILed this out, then multiplied everything by 2, subtracted 36 from both sides, in other words, to get my equation set equal to 0, and then I would have had to have used quadratic formula on it. So you can imagine it would be many, many, many more steps than the 4 I have written right here. All right. The next one I want you to try on your own, so pause the video and try it on your own, and then when you're done, you can start the video again and you can see if you got the correct answer. All right, so let's talk through the final example. I need to isolate the squared term, which is the x plus 5 quantity squared. So first thing I'm going to do is add 7 to both sides. Then I need to divide both sides by 4. So having done that, I'll get x plus 5 quantity squared is equal to 20. Then I have the squared term isolated, and so I can take the square root of both sides of the equation. Don't forget the plus or minus. The square root of the quantity squared is just the quantity, in this case x plus 5. And when I simplify the square root of 20, I get 2 root 5. And then finally, I need to subtract 5 from both sides. So final answer is x equals negative 5 plus or minus 2 root 5. Again, many steps would have been involved, similar to the last example, if you would have used a method other than the square root method on this particular problem. In the next part of this lesson, we're going to focus on solving quadratic equations with imaginary solutions. So I would like for you to pause the video and solve this equation, and then you can check your answer at the end, paying particular attention to if you completely simplified your final answer. All right, so let's talk through this one and see how you did. First thing we need to do is get our equation set equal to 0. We can't use square root method because we don't have just a squared term and a constant. So let's get our equation set equal to 0. I ended up just moving the negative 2x squared to the other side. And then if we try to factor this, it will not factor. So we're going to use quadratic formula. So opposite of b plus or minus square root of b squared minus 4 times a times c all over 2 times a. If we simplify underneath the radical, keep in mind negative 2, all of that's being squared, so I get a positive 4. From the negative 4 times 2 times 3, I get a negative 24. So finally, I get a negative square root of 20 underneath the radical. All right, then we want to simplify. Once we get this down to a single value, we want to simplify that as much as we can. So the square root of a negative 1 becomes I. And then to simplify square root of 20, that's 2 root 5. And then finally, we've got 3 numbers on the outside of the radical. We've got a 2 here, a 2 here, and a 4 here. All of those are evenly divisible by 2. So if we go through and truly divide 2 by 2 and 2 by 2 here and 4 by 2 here, we get 1 plus or minus I root 5 all over 2. Now that we know how to simplify negative numbers underneath a radical, underneath a square root, we want you to keep going with simplifying. So please do not stop right here now and say that there are no real solutions. You can now simplify this via an imaginary number, so we want you to keep going when you encounter this scenario in solving quadratic equations. In other words, make sure you simplify it as much as you possibly can including having an imaginary solution if that applies to a particular problem. All right, so in the next set of examples, we're going to sketch a parabola with the following. And we're going to sketch one where we have 2 real x-intercepts, one with 1 real x-intercept, and one with 0 real x-intercepts. And so we know an x-intercept is where, in this case, the parabola is going to cross the x-axis. So if we want to have a parabola that has 2 real x-intercepts, we could, for instance, have a parabola that's pointing down. And you can see here we've got 2 spots where it crosses the x-axis. We could also have a parabola pointing up. As long as it's crossing the x-axis twice, we would have 2 real x-intercepts. All right, in the middle example, we have 1 real x-intercept. So maybe we have a parabola pointing up this time, and it comes down, touches the x-axis in just 1 point, and then goes back up. We obviously could also have a parabola that's opening down and it comes up and it touches the x-axis in only 1 point and then goes back down. All right, and then the example on the right, 0 real x-intercepts means if it's a parabola pointing up, it needs to be above the x-axis. If it's a parabola pointing down, it needs to be below the x-axis. Either one of those is fine. And also, I did mention on the first example that I did over here on the left, yes, we could have had a parabola pointing up. Just as long as it touched the x-axis in 2 different points, it would have met the criteria. All right, in the next example, we're going to provide an example of a quadratic equation that opens down and is narrower than the parent function. And reminder, the parent function is going to be y equals x squared. It's the most basic quadratic function that we could have, and everything is in comparison to that. So it's similar to the concept that we did with absolute value equations earlier in the year. We compared absolute value equations to the parent function to figure out if they opened up or down or if they were narrower or wider than the parent function. So this is a similar concept. So an example of a quadratic equation that opens down and is narrower than the parent function would be something like this. Y is equal to negative 2x squared plus 3x minus 5. All right, so let's talk through the key components. The fact that this is a negative quadratic coefficient means that the parabola would open down. And then this 2 right here is what causes it to be narrower than the parent function. In other words, that 2 right there stretches it and as a result causes it to be narrower than the parent function. All right, and then an example of a quadratic equation that opens up and is wider than the parent function would be something like this. Y is equal to 1/2 x squared, and I'll leave the rest of the equation the same as the example above. So let's take a look at this. The fact that the quadratic coefficient here is positive is what causes it to open up. That 1/2 is more or less shrinks the parabola, so to speak, so it causes it to open wider than the parent function. So obviously there are many correct answers for these 2 examples, but these provide examples of each. And then the other thing I just want to emphasize is the fact that, again, this quadratic coefficient right here, whether it's positive or negative, and whether it has a value like a 2 or a 1/2 in there, that is what controls whether it opens up or down, narrower or wider, and it works in a very similar fashion to what it did for absolute value functions when we looked at those earlier in the year. All right, the next part of this lesson is going to focus on powers of I. So we've already talked about the fact that the imaginary number is I, and we're going to go through a little bit of an exploration process over here on the left before we look at detailed examples where we're going to evaluate things like I to the 214th and I to the 159th and I to the negative 17th power. So let's go through our exploration process first. So I to the 0, anything to the 0 is going to be 1. I is just I, all right? I squared, we know from a prior lesson, is -1 by definition. And then I cubed. Let's talk about how we could rewrite I cubed in terms of some of the prior values above, so to speak. And here's what I mean by that. I cubed could be thought about as I squared times I to the first for emphasis, because think about it. If we multiply something that has the same base, we add the exponent. So I cubed could be rewritten as I squared times I to the first. Well, we know from the values above that I squared is equal to -1. And as weird as this sounds, I is just I. So I cubed, in other words, simplifies to negative I. All right, now let's look at I to the fourth. So one way we could rewrite I to the fourth would be I squared times I squared. Again, if we are multiplying something that has the same base, we add our exponents. So I squared times I squared is I to the fourth. All right, well, we know that I squared is negative 1. If we multiply negative 1 times negative 1, we get a positive 1. Okay, so let's keep going. And there are many different ways now that we could rewrite I to the fifth. So one of the ways we could rewrite it, only one of many, is we could rewrite it as I to the fourth times I to the first. All right, well, we know from up above, I to the fourth is 1, a positive 1, and I is just I. So in other words, I to the fifth simplifies to I. And if we had used any combination of the prior I evaluations, so to speak, from up above, as long as our rewriting right here equaled I to the fifth, if we go through and simplify, we'll end up with the same conclusions over here. Okay, and we can pick any of them. There are many different combinations that would work. I'm just picking some off the top of my head. All right, I to the sixth. Let's look at that. Well, let's say we say that that is I squared times I to the fourth. All right. Obviously, the exponents match up, so to speak. All right, well, I squared is equal to negative 1, and I to the fourth from up above, we found out was equal to 1, so that's going to be equal to negative 1. All right, we're going to do one more. I to the seventh, let's say we say that's I to the fourth times I cubed. I to the fourth from up above, we found out was 1. I cubed was equal to negative I. So if we simplify that, that's just simply negative I. All right, and I should say before we come up with our conclusion is when, I'm rewriting I to the fifth, I could use more than just 2 of the I terms up above to rewrite I to the fifth, but I was just trying to do it 2 at a time, so to speak, simplify it a little bit. All right, now, all of this leads us to the following. Notice the pattern. We have a 1 and then I and a negative 1 and a negative I. A 1 and I, a negative 1 and a negative I. And if we would have kept going, you would have seen that that pattern repeats every 4, okay? So we've got it goes through here and it goes through here, so to speak. So again, that pattern of 1 I, negative 1, negative I, 1 I, negative 1, negative I, it would keep repeating every 4 terms, so to speak. All right, now let's see how that's going to help us. If we were to go through and rewrite, I to the 214th, using this process over here, it would be extremely inefficient, okay? So here's what I do. Since this repeats every 4, so to speak, I take 214 and I divide it by 4. All right, so we're going back to elementary school and we're doing good old long division, so to speak. So 4 goes into 21, 5 times? 5 times 4 is 20. If I subtract, I'm now going to be saying, okay, how many times does 4 go into 14? It goes in 3 times. 3 times 4 is 12. Remember elementary school? All right, and then we have a remainder of 2. Okay, well, here's how that's going to help us. That remainder is going to tie into our pattern over here via an exponent. So what I mean by that, we've got a remainder of 2. So go over here and look at my exponent of 2 and see what that simplified to, and this will indeed simplify to the same thing. So I to the 214th simplifies to negative 1. All right, now I tell my students the following. You need to know this pattern, and you need to show me this long division, okay? I will not take just the answer. If you choose to go through and rewrite these, because there's different ways of teaching this and learning this, if you choose to rewrite this so that you can then get to your negative 1 in another way, that's fine. But if you're going to use this method, you need to know this pattern, so to speak. You need to show your long division, and then you can come up with your final conclusion here. Again, tying the remainder into the exponent over here, knowing this pattern. All right, so what I would like for you to do is pause the video and try the next one on your own, and when you're done, restart the video and see if you got the answer correct. All right, so I did it over here where I had a little more space. So if I take 159, the original exponent, and divide it by 4, because that's what my pattern is, it repeats every 4, I'm going to get that my remainder is 3. And this remainder ties into my exponent over here for the pattern of I that I know. And that I to the third is equal to negative I, so that's what my final answer will be for I to the 159th power. All right, now for this next one, notice it's I to the negative 17th power. So the first thing I would do is just rewrite this as 1 over I to the 17th, positive 17th power. Then I would go through and do my division. So, 17 divided by 4 is going to give us a remainder of 1. So it's going to tie into my, I to the first over here. I to the first for emphasis right here. So if I come over here, this is going to be equal to, and I think I'm going to continue over here, this is going to be equal to 1 all over. Again, a remainder of 1 ties into a power of 1 for I, so it's going to be 1 over I. Now, we do not want there to be an imaginary number in the denominator, so now we're going to go through and rationalize the denominator. So we're going to multiply by I over I, and then we're going to keep going with simplifying. All right, and I'm going to work vertically here because I'm running out of space. So 1 times I in the numerator is I. In my denominator, I have I times I, which is I squared. And then finally, we know that I squared is equal to negative 1, so my final answer is going to be negative I. And again, do not leave any imaginary components in the denominator. Make sure you rationalize them. And then also, it's okay to have an I in your answer, but do not leave an I squared in your answer. Your I squared can be replaced with a negative 1, and then you can keep going with simplifying. All right, and let me just summarize before we go to the next thing. Again, you need to know the pattern, and you need to show your division to support your answer. Your teacher may have a different way of having you do these, an alternate way. You may know an alternate way yourself, but you need to make sure that you show your work to come to your final answer and not just write down, negative 1 or negative I or whatever the case may be. You need to make sure that you show work to support your answer. So either in the process that I've shown or in a rewriting fashion that either you know, or if you have a different teacher than me, that your teacher may show you. All right, then the final thing that we're going to do in this lesson is do some more examples off of that Making Practice Fun worksheet, but I'm going to focus on some problems that I've picked from the side that's labeled number 46. So I know in the prior lesson, some examples were done, mostly from Making Practice Fun number 45. I'm going to focus on Making Practice Fun number 46, doing some examples. And the ones that I'm going to do, I literally have the numbers from the worksheet. All right. All right, so let's get started. Number 5 says multiply 4i times 5i. So it's hopefully what you would expect it to be. We're going to multiply 4 times 5 and get 20. We're going to multiply I times I and get I squared. As we mentioned before, we don't want to leave an I squared in our answer. I squared is equal to negative 1, so 20 times the negative 1 is going to be negative 20, and that will be our final answer. All right, next example. We have a complex number being multiplied by a complex number. So we're going to FOIL it. So when we multiply our first term, we're going to get 5. When we multiply our outside terms, we're going to get 10i. Our inside terms, negative 7i. And our last terms will be negative 14i squared. And then we're going to go through and simplify as much as we can. So this negative 14i squared becomes positive 14. And the reason for that is I squared is equal to negative 1. So negative 14 times a negative 1 becomes a positive 14. So when I go through and simplify, I'm going to get 19 plus 3i. I'll take the 5 and add 14 to it, and then I'll combine the 10i minus 7i. So again, final answer is 19 plus 3i. All right, so I would like you to try the next example on your own. Pause the video, try number 12 on your own, and then restart the video and see if you got the problem correct. All right, so let's see how you did. When you multiply the first terms, 6 times 6, you'll get 36. The outside terms, you'll get 30i. The inside terms, negative 30i. And the last terms, negative 25i squared. Now we need to simplify. So 30i minus 30i obviously is 0. Negative 25 times a negative 1, which is what I squared is a positive 25. 36 plus 25 gives us 61. All right, when we look at the next example, which happens to be number 16 off of that Making Practice Fun number 46 worksheet, it asks us to find the conjugate of 6 minus 3i. So for a conjugate, we're going to keep the first term the same, so a positive 6, and then we're going to take the opposite of the second term. So originally it was a negative 3i, now we're going to make it a positive 3i. So the conjugate of 6 minus 3i is 6 plus 3i. So I want to go back to number 12 for just a moment and point out something. Here we had a complex number, and here we had its conjugate. So 6 minus 5i, the conjugate is 6 plus 5i. And notice what happened when we multiplied those together. We had a complex number be multiplied by its complex conjugate. And what happened was we ended up with a real number value. All right, that's going to play into what we're going to do with number 20 when we divide. All right, so on number 20, it says divide, and notice we have a complex number in the bottom. It includes an imaginary portion right here, and we've talked about the fact before that we don't want to have any imaginary numbers in the denominator. So we want to go through, and we actually want to rationalize the denominator. So what we're going to do is we're going to multiply by the conjugate of the denominator. All right, so the conjugate of the denominator in this case is going to be 1 minus I. All right, we keep the 1 the same, and then we take the opposite of the second term. So originally it was a plus I right here. Now we're going to make it a minus I. And then we know that what we multiply the denominator by, we need to multiply the numerator by as well. Because then what happens is we're essentially multiplying by the equivalent of 1. And that's okay. We can take this expression and we can multiply it by the equivalent of 1. All right, so now what we're going to do to keep going with simplifying, we're going to multiply everything in the numerator, multiply everything in the denominator, which is going to require us to FOIL. So if we FOIL in the numerator, if we multiply our first terms, we'll get 2. Our outside terms, we get minus 2i. Our inside terms, plus 1i. And then our last terms, we get minus I squared. And then in the denominator, we multiply our first terms, we'll get 1. Our outside terms, negative I. Our inside terms, plus I. And our last term is negative I squared. All right, now let's go through and keep simplifying and see what we get. Okay, so let's go through and simplify both the numerator and denominator as much as we can. Remember this I squared up here is going to be negative 1. All right, so if we go through and we simplify the numerator, we're going to get, we've got a 2 here minus a negative 1, so minus a negative 1 becomes plus 1, so we're going to have 3. And then if we simplify our I terms, we're going to have negative 2i plus 1i, so we're going to have negative I. All right, so if we look at our denominator, let's go through and simplify it. Again, this I squared is going to become negative 1, but keep in mind this negative sign right here, okay, is still going to get applied down here. So we're going to have a 1 minus a negative 1, so that'll become a plus 1 right here. So we'll have a 2 in our denominator. And then if we take a look at our I terms, negative I plus I, that goes away. So we have come up with our final answer right here. And there's a couple different ways you could write it. You could write it like I have it written. Some students will take it and write it as 3 halves minus, 1 half I. or even 3/2 minus I over 2. In other words, this 2 is a common denominator to both the 3 and the negative I. So there's different ways of writing it. I typically just leave it like this, but either of these alternative forms of the answer are mathematically equivalent, so they're fine as well. All right, one thing I wanted to mention though before I make my final comment is as follows. Notice when we multiply by the conjugate, we ended up getting rid of the imaginary portion in our denominator. So this is always a good thing to check right here. You can be in the ballpark or make sure you're in the ballpark if you no longer have an imaginary portion. Now, it doesn't guarantee that you did everything correctly, but it will at least get you in the ballpark, because if you still have an imaginary portion right here, either you did not pick the correct conjugate or you did something wrong in your foiling or combining like terms and simplifying, that type of thing. All right, and then the final thing I want to mention is just as follows. The last little section of the worksheet that you'll have to do for Making Practice Fun, number 46, is finding reciprocals. And in the prior lesson, number 25 was done in that particular lesson. And that was an example of finding the reciprocal and simplifying it. So number 25 was done in the prior lesson. If you need a little refresher, you could go to the end of that lesson and see how that was approached and finding the reciprocal and then going through and simplifying it. Okay, this completes the day 6 notes. Again, there was a huge variety of topics covered, but this does cover all of them and gives you examples in each of the areas that you'll be practicing in the assignment.